In this part 3 of Introduction to Linear Regression in Machine Learning, we discuss multivariable linear regression. So, just to remind that supervised learning is subdivided onto regression, prediction of continuous values of some parameters, and classification, prediction of discrete values. For example, classifying some object for the belonging to some classes of values. So regression and classification, we are considering now regression. And here we start dealing with a multivariable regression. It means that our features are no more just one scalar value, but it's a vector of some parameters. N parameters now is the dimension of our feature vector. And based, as is shown on the bottom, based on this feature vector of n coordinates, we must make a prediction y hat. So let us consider it in more detail. If in univariate linear regression, the prediction was just wx plus b, so here we no longer consider just one weight w, but we have a vector of weights w1, w2, etc., wn, and our feature vector is of the same dimension. And bias b remains, or intercept b, it remains only one scalar value. So now wx is replaced by dot product of vector w and vector x. So dot product, which means cross multiplication with the following summation of weight vector and feature vector x, as is shown here. So it's y hat is now dot product of w and x vectors plus intercept b. So we have to find the values of vector w and b, and now we'll consider one of the possible methods for doing this. It's a so-called normal equation, and for this purpose we make some trick. We extend the vector of parameters x by one additional coordinate, with the value of 1. And also we introduce the vector of parameter theta, which is combination of vector w and intercept b. So we now augmented the dimension of our problem by 1. So, and also variable y is now, as shown on the right upper part of the slide, variable y is now predicted as dot product of theta and x. Again, theta now includes both w and b. So, how to choose these coefficients? Yes, these parameters. Maybe this slide should precede the previous one. It would be more appropriate. So, how to choose coefficients? Of course, we must have training data. We have to have labels y, or target values, and we have to define optimality criterion. And the optimality criterion is still the cost function, which is the squares of the prediction errors, y minus double dot product of vector w and current feature vector x, xk, and also minus b intercept. This the averaging of these error squares of these prediction errors constitutes our cost function. So now we come to the normal equation. And I believe this one should follow now. Yes, we are augmenting the vector theta by vector w augment by b, intercept b, and we get vector theta, and x we augment by value of 1 and get augmented vector x. Now, what is essential for normal equation? This is a trick or a methodology which is very widely used in machine learning, statistics in particular. So we are making one big matrix X, the rows of which are the transport feature vectors. So vector x1 transport is the first row of this matrix. The second row of x is second feature vector is the second row of this matrix, etc. We have m n-dimensional vectors, so the dimension of matrix x is m by n. And vector y constitutes all our target values, all the labels. So in the ideal case, we would get that multiplication of x by theta is equal exactly to vector y. Yes, in ideal case, of course, in ideal case. But of course, we live in non-perfect world. We must find vector theta so it minimizes the cost function as shown on the bottom. This is the same cost function as was shown on the previous here. This is the same cost function, just written in another mathematically equivalent way. This is the same function. If we differentiate this function by theta, this cost function j by vector theta, in fact, we are calculating gradient. It will be useful for us in the following to calculate gradient descent. So we will get this derivative to 0. And finally, we get a normal equation shown on the right part. Here, normal equation, from which we can find vector theta by finding the inverse of matrix x transpose x, and then multiplied by transpose x and vector y. So finally, we can extract our desired vector w as the first n coordinates of the vector theta and b as its last coordinate of vector theta. Of course, there could be some problems with the inversion of matrix x transpose x, and sometimes we have to add here some regularizing term. Maybe we'll talk also about it in the future. So this is the idea of normal equation. Writing using a trick of augmenting our vector of features and also vector w by sb, and then we come to this normal equation. We find its solution. We get n plus 1 dimensional vector and extract weights as the first n coordinates and the bias as the final coordinate, the last coordinate of this vector theta. What I propose, we will look how it works in practice. Let us return to our usual car small example. We have to predict variable y, which is miles per gallon, consumption parameter of the car, based on the weight. This would be a first coordinate of the feature vector, and x2 horsepower, second coordinate of the feature vector. Let me move into Colab. I will load the necessary libraries. Also, I will load two coordinates, weight and horsepower. So we'll have 93 cars characterized by two parameters. So it would be, let me just print x, so I will show it. It's really so. X characterized by two coordinates. X is not defined. Why? Oh, because it's lowercase. Yes, it's lowercase. Okay. So the weight, yes, I don't know, in low bounds or in kilograms, and some acceleration parameter. So this is now, x is now a matrix of 93 by 2. 93 by 2. Okay, as usual, we subdivide our data into the training and test subsets. This is what I'm doing next. Also, data scaling can be useful, not for normal equation maybe, but it will not spoil the affair with scaling data. We talked about it in one of the previous videos. We can scale our data so it would have zero mean and unit variance. We can also plot. We can plot our data. Now scale data. For example, this is dependence of y, a predicted variable to be predicted, depending on x1 and x2 below. So we can see there is some possible linear dependency here. So these variables can contribute to the to assist the quality of prediction. So Normal equation, yes, we just program using the linear algebra operators the solution of normal equation, and we get this vector theta. Let us see what we have finally. Yes, we have solution for vector w, minus 0.66 and minus 0.24, and this is a scaled model. And of course, as I explained in the previous video, having received w and b for scaled variables, we can switch back. And get the w and b for unscaled data. And they are present. Here. W, two coordinates, and vector b. We have error for the training dataset and testing dataset, 3.66 and 4.33. Let us see how does it correspond to what we got in the one-dimensional case. Yes, in one-dimensional case, consider it in one of the previous videos, we got 3.81 and 4.41. So now for two-dimensional case, addition of additional variable, the using of additional variable, acceleration of the car, helped us to lower the error of prediction of the consumption parameter of the car, fuel consumption parameter, MPG of the car. It's now lower both for training data and what is more essential for testing data. So, but we can also consider adding another parameter, third parameter. Oh, it was not acceleration. It was the second parameter was horsepower. Now we add third parameter, acceleration. Excuse me. And we can expect that the error will be even lower. But it's not the case. I will write here already a solution. So the root mean square error for the training dataset really becomes lower, 3.49. Yes, it's lower than 3.66 for two-dimensional case. But the testing error is already higher. So this is such a phenomenon known as overfitting. Overfitting. We will talk about it in the next video in more detail. It's overfitting, and this is something which should be avoided. In this case, we understand that two variables are quite enough for the qualitative prediction of our target variable. So we consider it in this way: the solution or the finding of W and B in multivariable linear regression by normal equation. What are the drawbacks or disadvantages, maybe, or slight disadvantages at least, of using normal equation? It's quite computationally complex. We can see from the formula for theta that we have to inverse matrix which is n by n, which is n third degree of n, computationally complex. And while inverting the matrices, error accumulation occurs. We can encounter with singularity of this matrix, which is inverted. And also, of course, it's limited to linear problems, normal equation. And we will consider also as an alternative the application of gradient descent. Gradient descent, in the previous video, we discussed the essentials of the gradient descent. You can view this short lesson as well. So gradient descent means that our update is of the parameters W and B updates are moving in the direction opposite to the gradient of the cost function. The gradient shows the direction of the highest, of the quickest ascent or quickest increasing of cost function, and anti-gradient on inverse gradient with minus sign is inverse sign showing the direction of the quickest descent, quickest decreasing of the cost function. So we can, by analogy, write this equation. Now theta is now a vector. Yes, vector theta. It includes as well in our trick in the normal equation. We can say that it includes both weights of multivariable linear regression model and intercept b. So it's decreasing by gradient of cost function j multiplied by learning rate. As usual, learning rate regulates the speed of the convergence. So as usual, we have very carefully select this parameter. In fact, in some contemporary methods, this parameter even is selected adaptively at each step of gradient descent, but we are not considering here such a case. So we must calculate gradient. We can compare here the formulas for gradient for one-dimensional and n-dimensional case. Yes, everything is quite similar, except that just multiplying of wx is now replaced by dot product of vector w and vector x. So this is the difference. And correspondingly, updating parameters in gradient descent now looks like this. Also very quite similar. And of course, as we discussed in a one-dimensional case, also this equation can be vectorized. If we introduce the error vector E, bold E, which is shown here on the right, is this is matrix X multiplied vector W plus B minus vector Y. This is a vector of dimension M, yes, and we can write our updating equations for gradient descent as in the bottom in completely vectorized way, which is very efficient implementation. Of course, we can consider, I can propose to just look at one example in Python. I select here a very short artificial example. We have matrix X considering four three-dimensional vectors. Here I found the solution of the regression problem by normal equation. And we can very shortly, in a very few lines, we can define the equations. We can write equations for the gradient descent, solution of this problem by gradient descent. We can calculate each step the current error, which is multiplication of matrix X and vector W plus B. This is like a prediction, minus vector of target values Y. Now we can update W, we can update B, we can, if you like, calculate error, and finally we can have our desired vector exactly 1, 2, 3, and minus 2, b is equal to minus 2. Yes, which I artificially selected beforehand. So just to show this artificial example, to demonstrate this artificial example. So, but let us, we can also write it as a function. Yes, function, gradient descent, compute gradient. Yes, we can compute gradient. Here I already formatted is as a function compute gradient, and gradient descent is quite a short function which consists of computing gradient and updating W and B. So some kind of visualization. I also added the scalar, not vectorized implementation. We can later compare the convergence speed, work, the time of work for both functions. So returning to our example, what we now consider the two-dimensional case. Yes, let me see. We consider yes, two-dimensional case, weight and horsepower. So let us run the gradient descent. This is by normal equation. Now we'll run by, we will compile the function for gradient descent and run it with learning rate, let me see, 0.5, quite a high learning rate, and we get the same parameters, as we got by normal equation. So it gives the same answer, and here we can see also the graph of cost function. It very quickly decreases to one value and then remains in fact unchanged. Also here some script for comparing the implementation time. Yes, for vector implementation, here it's 550 milliseconds against 750 milliseconds. So in 15 times, the computation time reduced for vectors implementation of gradient descent. In one-dimensional case, if you remember, the reduction of time was computation time was only in three times. Here in 15 times. Okay. Is a complete function of linear regression. I think we can stop at this point. Just final remarks. So to summarize the gradient descent strategy, we start with some initial approximation for vector W and intercept B. We update them at every step, which we as expected must reduce the cost function, and until we get the minimum point. For example, the norm of gradient is now below some threshold, or maybe the values of cost function between adjacent iterations are very similar. So some stopping criterion is required. Again, in this for linear regression, the cost function has only one minimum point, so the local minimum is global minimum, so it can be found by gradient descent. In more difficult cases for multimodal functions, there could be several local minimums, and the question of initial approximation is of very crucial importance. Again, influence of learning rate is essential. One final moment, what I would like to mention is to notice the correlation coefficient. When adding new variables to consideration, for example, here we considered horsepower, weight, but we can also add here acceleration. The correlation coefficient between target variable y and parameter x, in this case, for example, weight or horsepower acceleration, can give us hint how much this variable can contribute to the quality of our prediction. So, for example, we can see on these graphs, two graphs for x1 and x2, there is some linear dependency, and correlation coefficients also show us this kind of dependency, of linear dependency. So, and 0.8 for first variable, weight, and 0.8 also a little lower for 0.9, let's say, and 0.8 now for the horsepower, but only 0.42 for acceleration. And as you remember, adding of acceleration did not improve the quality of our prediction, linear prediction. And I did not plot here dependency of y on x3 on, and I will do it now, and I believe we will see the difference. Let me do it right now. It will be 311, 312, and we will add 313. Yes, 313, we're adding one additional parameter. It will be third variable, index 2, and it will be x3. Okay. Let us see if it works. Yes, and you see that now these points, the mutual distribution of y and x3 is very scattered. It's scattered, and it shows that there is no potential in the of x3 to add some positive contribution into the prediction of y, in opposed to variable x1 and x2. So these all aspects should be taken into account. And thank you very much for your kind attention for watching this video.